Thomas. My name is Ed Kirtley. I'm the Assistant Dean here in the College of Engineering, Architecture, and Technology, and I'd like to welcome you to our first ever Student Professional Development Workshop. This is a program that we're doing in conjunction with the Student Council. Is Jonathan in here yet? Jonathan and Cole have helped set this up and get this going. In visiting with Dean Tucholsky, one of the things that we're committed to is helping prepare you to be successful professional engineers. When you graduate and you go out into industry, it is a transition. It's a transition both in probably financials, the biggest transition. You'll have money. But the other transition is really the mindset of you're no longer a student, you are a working professional in fields that are incredibly dynamic and very fast changing now. Most of you will become licensed professional engineers, and you will hold that certification, that licensure for the rest of your careers. And in every state that I know of, that's going to involve professional education. So our thought was to start introducing you to that whole concept of I'm a professional engineer and I'm going to have to learn beyond the scope of my job to keep that licensure and to stay proficient as an engineer. The other thing we were looking at is this is an opportunity for us to provide you opportunities for topics that we may not be able to provide within the regular curriculum. Depending on what engineering major you're in, it's probably 126 or 128 hours. That's very scripted, and there's not a lot of opportunities for you, especially hands-on labs, to do those things. So this is an opportunity where you kind of drive what the topics are going to be. Jonathan, the Student Council, has identified some topics of interest. Number one, right off the bat, was 3D printing. So we're going to be offering the topics that you choose. And again, so far, people have said we want hands-on experiences as part of professional development that maybe we don't have the opportunity to do in class. So that's why we're doing 3D printing. Just a little bit about this specific class. The response was so overwhelming that we'll probably offer the classroom and the lab again in the spring. We've got about 30 people on a waiting list. Thomas has been very gracious in working with us to get you as many opportunities as you can to get into the lab and get that experience. And if I understand it, those of you that attend the class tonight, that will get them a ticket to work in the lab. But then we also want you to have lab time so that you don't try to create something that blows up the 3D printer. Then you're mad, we're mad, everybody's mad, so we don't want to blow up the printers. But any questions about this series, about what we're doing with the program? And there's Jonathan. Jonathan, I want to thank you for your support and your vision with this. So there won't be any costs with these. I don't know what the other two topics will be in the spring, maybe hydraulics or fluid mechanics workshop. We don't know quite yet what they'll be.
But we're open to ideas if you guys have any you'd like to talk.
Yes, sir.
Quick question. How are you guys gathering ideas? Do you have some kind of something online where you can submit them, or how would you find it?
If you just email them to me, that'd be the best way, because it was kind of, me and Ed started talking and just brainstormed a few ideas, and that's sort of how it happened. So, yeah, we'd love feedback on that.
Yeah, that's whatever. Again, this really is your program. We'll be helping facilitate and manage it, but we want you to drive the topics and to be engaged and help us decide what you need extra training opportunities in. So, very good question. Any other questions? I want to go ahead and turn it over to Thomas. Thomas is a doctoral candidate in mechanical and aerospace engineering. And as Jonathan and I were talking about this class, we decided we'd do 3D printing. And well, who should we ask to facilitate 3D printing? And whoever we talked to, there's this graduate student in mechanical, Thomas Hayes. He's the guy that I'll be teaching this class. So we contacted Thomas, and he said absolutely. He obviously has a passion for this and a knack, and has gone out of his way to help meet your needs and make this an engaging opportunity for you. So Thomas, thank you for allowing us to do this. My office is upstairs in 214A. I don't get an opportunity to interact with students a lot. I teach primarily in the spring. So if there's ever anything that you need, anything that I can do to help, please don't hesitate to come up, and I'll do whatever I can to help you. So. No, I've got another thing to go to, unfortunately. Thank you.
So you said I was an enthusiast in 3D printing and kind of centered on that, but what I'm really centered on is the fact that students should not only just learn how to model things in SolidWorks in the class that I teach, not only learn how to analyze things on engineering sciences and learn how to lay out a design, but until you actually make one, until you make it real, until you have something in your hand that performs the action you've actually done nothing. It's not about concrete physical achievement, not just nice little paper products that look nice on the shelf or whatever. So that's what kind of drives me with 3D printing, is the opportunity to introduce students to products that are very real. Students like these guys who don't look like they've really done a lot of woodworking in their lifetimes can 3D print an entire aircraft. Now in this sense, the airplane isn't really all that novel construction. You see it's still built like you might see the schematic for any other RC airplane in the world. Also note which components are plastic, are 3D printed, and which ones are not. Landing gear, not 3D printed. Nose wheel, not 3D printed. Propeller, not 3D printed. High stress, high strain components people flat skip over with 3D printing. Some more advanced techniques can be to split your projects down so that you can use high strength components like carbon fiber rods to carry strain, and then use 3D printing to fill in the more complex pieces. Saving weight, not necessarily because the plastic is strong, but because you're able to avoid all the excess material. You're able to tailor the parts to exactly what you need. In this case, pressing everything out that isn't absolutely necessary. A lot of other disciplines are like 3D printing. You've probably seen this picture. It's been out there for a year and a half, 2 years. Fashion is really picking up on this because it's new, it's hip, and that's what fashion's all about. It's actually being practical. So, I mean, the very premise that you can make any shoe you want and have a little closet full of them just out of your maker bot entices a lot of people. But more practically, you can do things like athletic shoes, especially as you start to evolve the filaments and everything that go into printers. They're able to make tailored fit shoes for any person's foot. It's a very, very big thing, the combination of 3D printing and 3D scanning. In fact, one of the bigger companies, MakerBot, is trying to make a cheap version of both. So you can scan items, you can scan someone's arm, you can scan someone's foot, make a custom fit, entertain a 720S gold-plated shoe right there that looks super stylish. I'll wear them next week. All different styles though, again, like heels and just shapes you can't duplicate any other way. Well, technically you might be able to see, 5-axis CNC shoe like this. You're certainly not going to buy a 5-axis CNC machine for $500 and set it running in your apartment. For 3D printing, it's really opened that up to a lot of different kinds of people. Unfortunately, sometimes it gets carried a little bit far and just makes even the models themselves kind of question their path in life and what they're doing. But more practically, 3D printing, especially body scanning, is going to change a lot of things we take for granted. A 3D printed cast, I saw a picture of this, it just makes sense. It's one of those things that just works. If you ever broken your arm, and you see people like shoving coat hangers down outside it just to get the scratch they have, not required at all. Not to mention be way more comfortable and a smidge flexible. You don't get as sweaty, it won't smell as bad. You can actually take showers and wash your skin through the supporting structure. Not to mention, like I said, scan your arm, get a cast made, done. This type of technology will be printed quick, will be very effective. The target, the goal of 3D printing, far in the future, would be a printer that can print multiple materials, not just plastic, not just metal, not conductors, not just insulators, but all the types of materials you might need combined, like you see in the top left, like a stepper motor, combined directly with the structure, which is made of plastic, connecting all the wires and linkages you need to make so that the servo motors, the support structure, all of it is just one piece. Now, obviously, if you break a finger off this guy, it's completely broken now because there's no such thing as component parts anymore. But that's fine. If you can 3D print it, hopefully cost will be low enough, you can just replace the whole daggone arm. This is kind of the promise, the future of 3D printing, and the big thing that's standing in its way is metal production. Right now, cheap 3D printers don't really have access to making things high quality out of metal, much less combining materials inside the same print. But we'll cover that a lot more in the slides to come. More practically, you have a lot of prostheses using 3D printing primarily to fit the stub and the leg of those athletes or people who've lost a limb. Being able to make that complex shape, again, being able to scan something, not care how complex it is for manufacturing or for the fact of modeling it. And then throwing it on a person's foot lets them have lighter components that require smaller boots. They breathe better again. And the structures can be optimized to flex in ways that are more similar to what a human naturally experiences. But really the thing that's already happened is really changing a lot of lives are the cheap prosthetics. The fact that the guy who can't afford, a $50,000, super soccer leg, but his dad can go out and buy, a $400 made out of wood MakerBot, one of the original ones, for his son out, a very simple mechanical hand that he can actually just at least pick some things up or carry a bag at the very least. Changes lives. I mean, it's cheap, it's affordable, it's accessible, and the nice thing is, as you outgrow this hand, you just print another one. You scale it up, by an inch, say print again. If you want to make a screwdriver hand, go for it. You're basically literally Edward Scissorhands now with your 3D printer and any sort of attachment you want to put on yourself. But from the medical fields, you've all heard about like 3D printed or perhaps machine, hip replacements, shoulder replacements. In this case, it was an example where a person broke their neck, like an entire vertebrae just shattered, gone. They, using CT scans and MRI, printed out a model of what was left of the neck. The doctors were able to practice the surgery, take out the stuff that was shattered and broken, and then, based off that void, they generated a metal part, which filled in that gap. So before even cutting into the person, before having to put them through pain or whatever, and not having to leave their neck open for hours on end, they already had the perfect part to fit. They already knew how to perform the surgery. All of this from data they can get non-invasively through a CT machine. How do CT machines deliver data? Like whenever you get to see a picture of from an MRI or a CT, what are they called usually? Slices, right? Looks like you just took a person, put them on a meat cutter, and just slice them into chunks. That's actually perfect for 3D printing, because right now most technologies print in slices. They print in layers. I'm sure most of you already know that. Not teaching you too many new things. But as we go through more applications, this one stuck out to me a lot as a research kind of stuff that's been done. It was the trachea of a baby. It was very small, very small size. And then on the right is the actual part. The rest of the model is actually just the 3D, again, a 3D representation of the child's trachea. And as it was born, the one on the right over here was collapsing. Wherever they had that belt. In fact, this is a close-up of the belt, showing just how small it is. But the child kept on having a long collapse, wouldn't be able to breathe right. So, but the real innovative thing about this wasn't that they went in and implanted it surgically. It wasn't that it actually worked and stayed the child long enough to strengthen that pipe. It was the fact that after all that had been done correctly, this material was able to be absorbed into the body. They didn't have to go in and cut it out. It just simply dissolved, was absorbed, and was gone. So it just stayed there. They could do a surgery, put it in, leave it, not worry about it any longer. So material science is a huge, huge part of 3D printing. The medical side of 3D printing just completely throughout. Things like this used to be made out of metal. Things like that, they used to be kind of fit through a little bit of trial and error, and hammers on the operating table, and just all sorts of, Civil War type measures. But now, there's absolutely no sense. Now we just print out a 3D replacement for your head and let you set off every alarm between here and the airport. One thing that we print now, you see like a lot of plastic organs. But the direction this is going is to hopefully print out real organs. Get away from plastics, get away from just models or surgical prototypes. Print out lattices, print out structures that allow a researcher or a scientist to seed them with a person's own self. Like say your heart's going out, your kidney's dying, or you've enjoyed college too much and your liver is just gone. You could potentially regrow a structure for that liver, seed it with originating cells, and let cells do what they do best and just replicate. The structure, the vascular blood flow through that organ is really the barrier. So, I mean, it is not unfounded at all to think that we could potentially manufacture organs for you, for your body, with your DNA, from your guts, for your guts. That would revolutionize everything. It's a big deal. That's like one of those holy grail targets. We'll see if we get there or when we get there. It's probably like, fusion, where it's only 5 years away, 10 years away. We'll see. It's a moving target, but it'd be revolutionary to say the least. Mentioning vascular systems, there has been one paper published semi-recently that a team has achieved. They successfully were able to emulate a very complex vascular system of the liver, not by actually just including the pipes or the tubes inside of the liver itself whenever they made it, but they actually included threads, like little tubes inside there that once they were done with the print, once they were done with the structure, they were able to withdraw those tubes or otherwise dissolve out the larger ones, leaving voids, leaving pipes of the super complex nature on the right. And that's the problem with these organs so far. It's not that we can't make them, it's not that they can't replicate, it's just we can't let them breathe. We can't give them the nutrients they need. They kind of die off quickly, as best I understand. I'm not a bio-engineer, so I'm speaking a little bit out of my discipline here, but as best I understand, that's where we kind of stand on that. So, we've covered applications. The rest of the things we're going to talk about today are types of 3D printers, because FDM, finite deposition modeling type printers like you see MakerBots and everything else that's cheap in dorm rooms on campus, is certainly not the only style. There's tons of 3D printers of all different price points and everything else you might want. We're going to go through an overview of those machines and how much they cost, because that's a big part of it. What online printing services exist. If you really, really need to get something printed out of stainless steel, you can't machine otherwise, you have online services you can go pay $500, $600 to get your part manufactured for you. They own and operate those large, expensive machines, and it's not really a bad deal. We'll get quite in depth on FDM printing, because that's the kind of printers we have on campus. We'll discuss the problems common to that style of printing, problems you might have tonight as we go over to the printer. Then we'll get specific to the actual printers we have, the SolidDoodle 4 3D printers. We actually have 10 of them in the lab across the street. There's, I think, 5 MakerBots at the DML, 1 MakerBot in the library. It's a partridge in a pear tree somewhere. And lastly, we'll go over kind of this program called Repeater Host. It's open source software that drives a lot of FDM printers. It's actually what generates G code to maneuver the print tag around on the platform and get things done. I like to say, if you have questions, you have comments, I'll stop and answer things as best I can at any point. Just raise your hand if you have questions. It's not a super formal thing. It's not just a lecture one way. We'll get this thing taken care of. So this first part will be about an hour. We'll pause for 5 or 10 minutes for people to get sodas, drinks, bathrooms, whatever. Then we'll get into Repeater Host. I'll show you that in here, because once we get to the lab, it's not going to be a great environment for me to kind of put my hand over your shoulder and show you how to use software. We've actually got Repeater Host running up there on the second laptop. Switch over to that while you guys are getting a snack, and we'll go with that. Then the second half of the course will be all the printing. We've actually got a little model made specifically for this course. Went over there and printed a couple of them out last night. There you go. Show them this when we pass on around, but it's just a little OSU. So it's pretty nice little thing. This one here takes about 30, 40 minutes to print. The little one takes about 20. So initially you see the 3D printers aren't super fast, but you'll get some unique access to the printers yourself. Moving on, the different kinds of 3D printers we have. This list is something to remember, because you hear all these abbreviations because nobody wants to repeatedly say direct metal laser sintering or laminated object manufacturing. It's just long. SLS, SLA is a lot easier to discuss. So the most common, your MakerBots, the SolidDoodles, everything you see on TV that's squirting out plastic like a hot glue gun. That's FDM, also called FFM. FDM is finite deposition manufacturing, fused deposition modeling. People use different abbreviations. FFM is fused filament manufacturing. Same thing, different name. SLA, stereolithography. That's one of the older technologies. In the 70s or 80s, a lot of industrial companies use that for several decades now, at great expense when it first came out, but still going strong. SLS is selective laser sintering. In my opinion, one of the more promising methods of 3D printing. DMLS is very similar to SLS, except that you're doing it with metal. DIW is direct ink writing, which has problems we'll discuss when we get into things. Electron beam manufacturing is the same pretty much as the laser methods, except you're using a cathode ray tube, essentially using an old television style electron beam instead of light to heat up the filaments. Lastly, laminated object manufacturing. So, first up on the list is finite deposition modeling. Like I said, MakerBots, these machines just move primarily in X and Y coordinates with all the danger of a hot glue gun. I mean, if you hurt yourself using the machines at OSU, you should probably hang your head a little bit, because I think junior high kids use these successfully without burning their eyes out. So these do go down layer by layer, and they do what's called slice the 3D model. All 3D models are imported as STL files. That originally stood for stereolithography, which shows you where that technology is situated in history. But layer by layer, they lay things down, generally printing about 1 cubic inch an hour. It's not fast. That takes a while. In fact, you see one of the things they do to make printing faster is they automatically include voids inside the part. This is a rim it's printing out. You see the periphery of it is mostly air. The slicing software automatically detects regions which are otherwise solid plastic, and generally, unless you change the settings, will replace that with honeycomb. We'll replace that with other things. If you look at the back of this, you can actually see the honeycomb inside of it that the slicing program did automatically to save time and save plastic. You can't disable it, make it solid if you want. But anyway, moving on.
Quick question.
Sure.
What's
Pause.
the,
Pause.
what's the maximum resolution you can have at FDM?
That is actually a good question, one that comes up a lot. FDM on our machines can print out 0.1 millimeter traces. It's possible to do that. Now, another thing you should ask is, what's the minimum wall thickness you make? How thin can you make a single vertical wall, which is usually going to take a couple of traces worth of thickness. So about 0.2, 0.3 millimeters is about as thin as you can make a wall with the settings that already exist over there. All this being said, for the guys, I think we had some students last week just printing out at 0.1 millimeters. They're all kind of asleep and bored because they've been there the entire day and the part still wasn't done. If you print out at the default, which is 0.3, that's the default for those printers, which has worked quite well. That's what these parts being passed around are printed at, is 0.3 millimeter trace. That part would take 30 minutes. Now, if you just, for the sake of simplicity, model that trace as a square, so 0.3 millimeter square, and then you switch to 0.1, how much longer is it going to take you to print? Just for the sake of time, we know it's going to take 9 times as long, right? Because 9.1s fit inside of a 0.3. So really you take a 30-minute print and turn it into 270 minutes, if I can do math live in front of people. So it takes a long time whenever you just decrease that one little parameter. So yeah, you can increase the resolution, but it comes at great expense of time. You're not really going to accelerate how fast the head moves around, which is the big limiting thing for those FDM prints. No sweat. Questions like that are great. Feed it into me as you want. All right, SLA. This is put together by a company called Solid Concepts. They just had a slick video on YouTube, so I ripped it off of them, but left their logo. But SLA cuts, slices the model just like FDM does. These machines are generally more expensive. This technology has existed for a number of decades. But interestingly enough, the build platform descends into this pool of ultraviolet reactive fluid. So the UV laser is actually steered down onto the fluid. You'll see the little motors that steer here, the voice coil actuators that steer the lasers, just actually mirrors that move it around. The laser itself is stationary. And by using mirrors, instead of having to accelerate the big laser head, they actually steer this around incredibly fast. Like you can lay down a layer fairly quick, and that's actually good because each layer is extremely, extremely, extremely thin, like 1/1000 of an inch thick. Like stupidly thin. The reason I have to wipe across the part every time is just to make sure it has a thin layer of liquid ready to be hardened on the surface. Once that laser hits it, hardens the plastic up, and eventually after, hours and hours and hours of this, you pull your part out. Now, as you pull these out, they're still not completely hardened. You actually have to put them in a UV oven. Basically just an easy bake oven with UV lights that cooks the parts, hardens it all up, then you have a usable piece. SLA, I'll just play it again while it's going. SLA has been used for wind tunnel models. It's one way to get an extremely, extremely smooth surface on parts. If you just even put a coat of spray paint on it and sand it down, you also have something very, very, very soft and smooth to the touch. Because each layer is so fine, you can't even feel the difference between the layers. So, SLS is similar, as we transition here, except instead of using a liquid, you're actually spreading a powder down. It's still laser centered. It's still a laser that heats the object up, the material up. But again, instead of using a liquid bed, that little square part descends as it builds. You are using a powder almost as a fluid in this setup. So see how the guy actually gets the layer started? I mean, you don't have to sit there and do that every time. The machine obviously does it for you. But it's actually really neat to see the laser come in, center that plastic together. That's kind of the difference between DMLS and SLS. Plain SLS is a plastic powder. Just the heat of the laser causes it to fuse with the particles next to it. And again, like you see here, after the part's been sliced with very, very thin layers, you can put things together however you like. One drawback as we discuss all these powder-based systems and also SLA, the liquid-based system, is that say you wanted to model a tennis ball. Here's a 3 model tennis ball. It's important that it's hollow, right? If you made a perfect sphere that was hollow, how do you get the liquid or the powder out of the middle of it? You have to drill a hole. So that's one drawback. Making sure you don't have voids that contain the powder. You actually see how ever so slightly the laser's etching that in, laser new layer material down. But having to have a method to get the powder out of enclosed spaces inside of the 3D printed part is one of the bigger challenges for SLS, SLA, all these kind of big vats of printing. Also, this part's kind of tedious. The post-processing work, you have to pull out the entire powder bucket, and then somewhere in there is the part that you made. Company called Solid Concepts, I believe, does a lot of this style of printing. They actually can do it in color. They apply ink at each layer as they center it together, as they glue it together, essentially. But they have software that, after all their customers on the internet, you upload hundreds of models. They say, okay, this is what we need to print today, and the software will orient these models in all 3 axes, actually 6 dimensions, 6 degrees of freedom, to maximize the amount of parts they get out of this volume. So basically, once a day, they run that machine and print the entire volume with an optimized set of parts located inside it. That was pretty slick in their video. I probably should have shown it here. But you see that there's post-work involved in almost every kind of 3D printing. In this case, you have to dig out all this powder, which can sometimes be very, very well compacted inside of it. That's one of the things you want to look at as you decide what kind of 3D printer to use if you're in industry, is look at the potential post-work involved. So let's get on to direct metal laser sintering. As far as utility, this is probably one of the most useful 3D printers available, one of the most useful styles. Unfortunately, it's also one of the most expensive. The biggest drawback with plastic 3D printers, yeah, they're cool, yes, they can make any part you want, but the big drawback is that every part you make is reasonably weak. Unless you go through some other processes, unless you use some extremely advanced materials, even SLS parts aren't the strongest things in the world. But DMLS, they can actually work with materials that are otherwise extremely hard to machine. You can direct metal laser sinter materials that are extremely taxing on even the best CNC machines, even taxing on some of these other high advanced machine tools. Because the thing is, there's no stress on a part. You're just melting the metal. So as long as your laser gets hot enough to melt titanium or Inconel or cobalt chrome, you can now make parts directly. Like you can make a heat exchanger with extremely thin walls, intricate pathways, directly out of cobalt chrome that you put in the path of a flame, you get massive heat transfer coefficients. If you try to manufacture any other way, it's just not going to happen. So the fact you can use very high-end materials, very high-end metals, and it just pops out a finished part is really nice. Obviously, the downside to this is it's very expensive. That's the trade-off. Even the powdered metal is not cheap at all. You're basically buying a big block of titanium, which is never cheap. The Russians are finicky about that. No questions on these? Going down the list? Cool. One question whenever you want. PolyJet. This is actually the closest thing to your inkjet printer. It uses inkjet printer heads, that same technology, but they can actually print out different materials from this big print head going across. They actually have different inkjet heads. Some can print plastic. You can set some up with like a rubber type material. So you'll see in this video later on, they have examples of single parts that have different materials embedded inside of it. Again, you saw the Z layer height there, half a thousandth of an inch. So there's a 0.0006, 306. The downside to these type of machines, you can see by their size and their really, really purposefully built nature, that they're not cheap. You have to buy all of your supplies, all of the ink, all the plastic, the reservoirs you see down there at the bottom, from the company that built you the machine. Just to give you a sense of scale, whenever you deal with proprietary materials versus open source, a roll of plastic that you can use on like a rep wrap or the solid roll here costs $35 on Amazon. A roll of plastic from Solid Concepts, Stratasys, costs $1,000. It's actually shorter. There's not as much on their roll either, but they have engineered it and studied it. Whatever, you just want that. But these parts are actually really, really precise. It's interesting because they can print out materials that dissolve. That's one of the big differentiating things in some types of plastic printers. You can, using this inkjet technology, lay down material that after soaking in water lets you make hinges directly. I mean, you don't have to put hinges together. It came out of the machine like that. Once they washed away and dissolved the material that was supporting everything together, it just came right apart. Let's see that. Yeah, so another thing is, notice, I think he's pointing out here, how small the layers are. So that's the size of a dime. You just barely see the Z height. If you have that little OSU being passed around, you can definitely feel the layer height on that. It's much different, so 0.3 millimeters. That second part was an example showing two materials in the same thing. So capability-wise, these PolyJet printers, inkjet printers are really, really up there. The downside is that once you go out and print a cool part, and then you come back 2 weeks later and print out another cool part, you get to replace every single inkjet head. Because when they got cold, all your plastic solidified in them, and yeah, you're done. These inkjet printers also work for, you'll see some of them work with cornstarch. Instead of plastic powder, they actually just use a cornstarch powder, which is cheap, but it's the same thing. Instead of spraying plastic in that situation, they spray glue. It's much like SLS. But instead of sintering things, they actually just stick it together. Same problem there. The print heads, once you're finished with them, glue themselves together, and we all know the most expensive part of a printer, or at least an inkjet, are the stupid print cartridges you have to buy every 6 months. So that very quickly becomes the governing expense of those type of printers. It's not the ink, it's not the glue, it's not the printer itself, it's rebuying these inkjet heads every time you have to print. So be cautious of that if you ever are asked to buy a 3D printer for some sort of organization. This one probably looks the coolest. Electron beam manufacturing. If something's out of Star Trek, this is it. You have to use this in an inert atmosphere. Like inside your television, the reason those old cathode ray tubes were so heavy is because they had very low pressure inside. There's near vacuum. So these actually operate in an inert atmosphere, and so does direct metal laser sintering for that fact. But instead of using a laser to sinter things together, these actually just, they use an electron beam. Just like you used to have scanning on a cathode ray tube television, these steer and change the magnitude of this beam to print out any sort of magnitude of part. I mean, it looks very stark and very flashy, but otherwise operates very similar to DMLS. Hardens a layer of powder, the whole vat sinks down into the printer more, spreads a new layer of powder out on top, hardens that one, and so layer by layer you make as complicated parts as you like. And lastly, we get to the poor old laminated object manufacture, which you can even tell by the era of this video that these printers started off quite popular because the material was cheap. You could literally, some of these worked with printer paper. Basically just cut out shapes out of printer paper, just glue them on top of each other until you had the part you wanted. They're reasonably strong, pretty cheap material-wise, but they've been surpassed quite a lot. But it's still important to cover that. So in this case, that spool of material you saw put in the front was his roll of printer paper, essentially. So it lays it down layer by layer, etching out or cutting out that material, gluing it together, and then by the end, you can see the poor guy having to peel apart this piece with all the extra plastic that isn't required. It requires a whole lot of post-processing to get this to work. So this type of technology is not only material intensive, it's not cheap. It requires both glue, specialized paper. While it does move the print head around a little bit faster than FDM printers, it's still going to take a long time to print anything out because the sheets you lay down per layer are not very thick. So it's actually just cutting it, slicing it. You can't apply color in certain circumstances. So I want to get to the part where it shows the guy having to peel the thing out. So you pull out this whole chunk of glued together plastic sheets, and then somehow know where to start peeling. It's like trying to open an old CD case. If anybody remembers CDs. You just start taking out layer by layer, and then you keep pulling and keep peeling. You notice how they're doing time lapse here, because he's been doing this for 4 hours at this point. And then you're left with a small part. And so that looks perfect, but I'm skeptical of how useful that thing actually is. So anyway, that's kind of a quick overview of the major types of 3D printing. You got questions after that? Yeah.
More of a comment. They took a metal laser 3D printer into space and it printed rockets with it. And
Yeah, is that the one they sent up to the space station? I thought it was FDM, but I'm wrong.
No, well, they probably sent FDM a while ago, but
Yeah.
now they have laser rocks up there to do replacement parts. So if they just send the data, they can fix it.
Yeah. You said they use a DMLS, right? Direct metal laser sintering on the space station to make replacement parts. And the reason I would say they use DMLS instead of a FDM machine or something else, if you're going to pay to put that on the space station, it's very valuable real estate. You're going to make sure it's a 3D printer that's going to make something useful for you. It's the point I'm going to try to reincarnate or reiterate today as we go through this, that plastic parts are cool. Plastic parts, it's neat to make whatever you want, but in the end you still end up with a piece of plastic. The holy grail, the thing that the researchers in this room should be going for, especially the metallurgists and the material scientists, are to make a low-cost metal 3D printer. You heard it once there, you're going to hear it a lot more. Let's keep going. Cost. So you saw the really expensive Stratasys SLS machine. Let's buy a bunch of them. $846,000 each. SLS, at this point, it did recently expire, but it was patented up until just a few months ago. It actually expired, I think, June of 2014. A lot of people were saying oh, it's great, with this patent expired, it'll come down in price extensively. It hasn't really happened yet. Still, even without the patents owned by Stratasys, the cheapest SLS machine you can get, even printing a small scale, is still like $36,000. So, yeah, it's probably better at this point that if you need something made of SLS or DMLS, call up Solid Concepts, call up a company that does this for a living, and have them make your $700 part. You make 1,000 of them by the time you pay for the machine itself. They're cool, they're very useful, but research needs to be done, the market needs to be opened up to make them a lot cheaper. So Stratasys Jet printer, that's the one you saw, they can lay down different materials, $330,000. Notice that that's very much the industrial scale, the industrial size of machines. When I was at Lockheed, they had a wall full of Stratasys printers. And now that I see how much they cost, I kind of shudder because they didn't work very well. They kind of just wasted their cash. And now we do the same thing over across the hall with, $500 printers. This is very much, technology is moving quick. It's just like computers. I guess they still are a little bit, even more so at the turn of the century, where you buy a computer, 2 years later, it's pretty much obsolete. 3D printers are working the same way right now. If you bought an $850,000 printer, that technology is going to cost, $15,000 a couple years after you buy that. So be careful with your investments at this point. The cheap SLS printers, like you see over here, it's called the Norge. It's kind of a funny name. I think it's European. But that shows you the scale of things. It's actually it's about that tall. It still requires an inert atmosphere, so you have to hook up an argon or a nitrogen bottle to it. There's another expense. But it works. You can laser center things, but it's still 30K. And then lastly, FDM printers. This is the stuff that you've seen popularized 3D printing. It's been on the episode of Big Bang Theory. All sorts of different things. You can make them as cheap as $250. You can go on eBay and buy a Prusa Mendel RepRap kit, put it together yourself and stuff you find at Lowe's, and $250 later you're 3D printing something that's probably kind of mushy and wrong, but it'll work. Up to $3,500, $5,000. Some of the MakerBot stuff's getting pretty advanced, pretty expensive, especially multiple head printers, multiple color printers. You can add all sorts of options to these things. Automatic bed leveling. They're actually starting to add bells and whistles. That takes the price up. But we'll cover all these different kinds of printers here in a little bit. If you are getting a little bit of sticker shock while looking at DMLS printer, keep these guys in mind. Solid Concepts, Shapeways, Protolabs, all sorts of other services online. In fact, I think there's even a company in Stillwater that's started by students that does plastic 3D printing. I think one of those guys, he's not in my class, but I always see him in the computer lab. He's always promoting his business. So you can pay the guys right off campus to print something for you out of plastic. The nice thing about paying someone else to do this is it's reasonably low cost, especially if you want to print something out of like this sandstone material. Full of color sandstone, they can apply ink to it. It's built kind of like SLS, but instead of laser sintering, it's put together with glue. But because of that, they can apply ink at every layer. So you can literally just print out, keep your money right. You can go on to use things as exotic as steel, cobalt chrome. In fact, Shapeways, which this image is from, I have to give them credit for it, can print stuff for you out of gold. So if you want your name in big gold letters for a necklace, that's it. It's the price of gold plus the price of their print. They actually do it through a lost wax method. They don't directly print gold. They directly print a wax model of what you want, and they go through the process of molding that. But it's still kind of cool. You can go on the internet and order anything out of gold that you desire. So, something else that's quite useful, ceramics. I mean, just kind of look around at bronze, brass, and this is the real stuff. This isn't plastic with embedded chunks of bronze like we'll cover in a bit. This is solid, heavy bronze. If you want a high-performance heat exchanger with thin walls that you can throw inside of a flame, which might be part of my research and why I keep going back to that topic, this is the way to do it. It's going to cost you several $1,000s, but whatever. It's awesome. Castable wax. You can also make, if you're going to do the molding process yourself, so you have your own supply of gold buried in your backyard, you can order the castable wax piece from them and then do the casting process yourself. Oh no, I'm dropped off. I think it's what's going on here? But in the desire to make this cheaper, in the desire to not be dependent on online printing services that own DMLS printers, this guy, Prusa Mendel, was one of the first to set out to make kind of a self-replicating FDM printer. I mean, this is old. This is like old technology. It's done with Arduinos and stepper motor drivers. It has multiple iterations of the driving circuitry and boards. But the nice thing is that other than the all-thread rod you see there, every little light component is 3D printed itself. So what people will do is build one of these printers and then set about 3D printing kits that then they sell on eBay for $30 a piece and pay for all of the materials they use to make the printer. So the printer is kind of self-replicating in a sense that you can basically earn back the money you invested into making it by making somebody else's printer parts for them. Obviously things like the heated printer bed, the circuits, the drive belts, stepper motors, there's still a lot there that can't be 3D printed. That gets back kind of to the implications and the research direction you might want to take in advancing this discipline. making printers that can print more than just plastic is going to be a big enabler. But the big thing that's limiting FDM is being able to print with metals. You've heard me touch on it like 2 or 3 times already, and this is actually one person's study where he made his own alloy. He kind of dove into the material science of things, even himself acknowledging that he had no idea what he was doing. He just looked at a bunch of charts, read a bunch of those boring ASTM books in the library. They're gate thick. And the key is to recognize that FDM depends not on making something into a liquid. You're not taking the plastic and liquefying it. You're taking the plastic and turning it just on what's called the glass transition temperature. It's still a solid, but it kind of flows. It's rubbery. I mean, don't sit there and play with it. You'll burn your hands. But it's not yet a liquid, but it's not exactly behaving as a solid either. It's in a transition region. So if you can make a metal that can exhibit similar properties in the transition between solid and liquid, you could potentially use that filament in FDM printing. If you pull that off, you're going to make a lot of cash really quick. People are going to buy that stuff up as fast as you can make it. This gentleman had limited success over here on the left. Looks kind of terrible, but most first articles do. Trying several different things out. He used this mixture of indium, silicon, and bismuth, I believe, giving the proportions there that's cut off by the projector. If you actually consult this presentation, which we'll probably send out to the mailing list for this class, you can follow the link, read up his article. It's actually a pretty neat thing to read. But it would be entirely possible, in my opinion, to make metal filament and print out of a 3D printer. Just nobody with the metallurgical skills has done it yet. So chemists, metallurgists, get at it. Other ways to make metal prints. This company ColorFab has done this with a couple different kinds of metals, copper and bronze. They take plastic PLA film, which is really common, so a lot of people print plastic stuff out of, and fill it with a bunch of metal powder. So when you pick it up, it's not heavy like a piece of metal. It's still fairly light. It's somewhere in between. But the nice thing is that at least graphically, even after it prints in a very matte finish like you see here, you throw it in a rock tumbler, you polish it up, and you get a very smooth sheen to it. It has that metal look. So if you wanted to have a fake, bronze bust of yourself on your desk as you conduct research, you can do that. I don't have one of those. No, I don't. I really don't. It'll be fun though. So anyway, ColorFab's metal filament, it's really just an aesthetic thing. We're not there printing metals out of a 3D printer, but it's really cool that you can at least make it look that way. If I didn't tell you that wasn't real metal, you'd probably believe it. So right now, the only way to really achieve full metal by using a 3D printer is doing a lost wax method. Print out what you want out of the printer, put it on screws like all the Yoda heads here. This little plastic piece in the middle is called a sprue. That lets you make more than one part in a single molding pour. And then basically you just rip away the plastic when you're done, and out pops your metal piece. If you've done it right, or if you've done it wrong, you just have mixed together metal and plastic. You can do this either way. You can go directly about manufacturing the mold out of plastic and pour a hopefully low melting point metal into it, so that it doesn't annihilate your mold. Or you can go the opposite route, like in the Yoda figurines, of actually melting out the plastic once you've made the sand casting mold, and pouring the metal into it. So any sort of the classic sand casting methods are perfectly viable. You can see there's a lot of successful stories out there on the web. This is really the only truly successful solid metal part making method for 3D printers we've got right now, unless you want to go spend a bunch on the MLS print. But talking about what we can actually use in the printers here, the two big ones, ABS, PLA. ABS plastic, acrylamide, butadiene, styrene. Whatever that means to you, that's really where 3D printers started. That's a very common plastic, but the problem that arose with it is that it's just hard to use. One of the big problems with 3D printers we'll touch on is that it's hard to get things to adhere to a print bed. ABS is really hard to get to adhere to a print bed. PLA solves a lot of those problems. In fact, the things you'll be printing on today will be mainly PLA. Those parts passed around, PLA. They have all sorts of other filaments you can buy and put through printers. They have plastic that is flexible. It's still based on a PLA formula. And even after printing it, it's still a rubbery texture. If you want to print out treads for a tire, that's it. They have things called lay wood and lay brick. It's kind of a trade name. But again, it's a plastic material that has wooden, basically sawdust embedded into it. Or the other one has chalk. So it comes out looking like a ceramic. So you can print out essentially like a little pot. If you want one little flower put in it or something. And it would look like a ceramic pot coming out of a 3D printer. Again, you don't get the properties of wood, you don't get the properties of ceramic, it just looks and feels that way. So these are very much cosmetic results. And for nylon, PVA, Bendelay is a strong 3D printing material. TPE is actually useful because that is again, a rubbery material. That's one thing that one material that prints quite well. You need friction, you need traction, you need flexibility. There are multiple flexible options you can 3D print. One thing other researchers lean to are conductive fibers for 3D printers. Some 3D printers have multiple print heads, so you could have one with ABS and another with conductive ABS or PLA. So you can literally print circuits in 3 dimensions throughout your part. You can embed the connections for your RC car into the RC car structure itself. That's really their goal. We're not there yet because everything has really high resistance. In this case, 1200 ohms per centimeter. Not great. Then lastly, one thing that just is crazy is lay foam, or lay foam, however you want to pronounce it. It's literally like a sponge. You 3D print it, dissolve away the supporting plastic. It's a water soluble, and once you pull back out of the water, it's just a very soft, flexible, bendable sponge. I don't know why you want to 3D print a sponge, but if you have a need to, it's really cool. So yeah. What we have is pictured down here in the bottom right. Solid noodle floors, and the reason we bought those were that when I priced everything, I looked at the market of printers at the time. They had a reasonably large build volume for FDM printers, 8 inches cubed. So any part you want to make, a single go, needs to be within 8 inches cubic build volume. These are primarily bought, in this case, to support engineering design, 1332. It's a class of 330 students, which is split into teams. I know a lot of you have been in my class. I see familiar faces in this room. So we actually bought 10 of these, I wouldn't say lower, we'll say lower capability printers. They're single print head. They don't have some printers have the ability to print support material at the same time they print ABS with 2 extruders. These just print a single material at the same time. But they do run open source software. They are connected to a computer, whereas some 3D printers allow you to throw a flash card into them. Generally, that upgrades about $500. So I might as well look it up to a computer if you want. That way you run SolidWorks and everything else you might need to make the 3D file right next to the side of it. So anyway, like I said, everything's run by repeating your host on these printers, and just like you saw in the video, they just go around spaghettiing out plastic to make the parts you want. Common problems with this. You've heard me mention warping of thin parts. I've had a lot of student teams have nothing but trouble with ABS. I've had trouble with ABS myself. And in fact, it's one of the few reasons these printers have a heated print bed at all. That's one of the tactics that makers and designers will use. The bed you build on will warm up. It's a prescribed temperature. It actually has a control system on it to keep it at a specified temperature, usually 105 C, which seems hot, but for whatever reason I haven't scalded myself on it yet, although I've touched it a lot. That heating the print bed helps keep the part from warping as much. Now I've tried several different things. I've tried several different materials, different print bed temperatures, different connections, and ABS invariably always just causes a headache. You'll be halfway through your print, something gets snagged a little bit, the whole part comes loose from the print bed itself, and then there goes an hour and a half of your time. Because once that part comes off the base, you've lost your zero, the printer doesn't know how to continue post. PLA is much more forgiving. In fact, one of the best materials to get PLA to adhere to a print bed is high dollar masking tape from Walmart for like $1.50 a roll. So that's what we use in the printing lab. You know, our high-tech supply is masking tape, 2-inch wide masking tape, just cover the print bed with it, good to go. The high-tech printing material used for ABS is Kapton tape, which one roll of it is like $80, the cheapest you can find. If you just search for a quick internet search, you're going to spend $400 on a roll of Kapton tape. The stuff's not cheap. They like to use it in space. Things they put in space often carry a good price tag. So anyway, getting the parts stick to the print bed is the single biggest challenge. Yeah.
Just to be clear, you're not sticking with the sticky side, not the
Sticky side down of the Kapton tape, yeah, both for the masking tape and everything else. One of the other things you see listed here that I've tried is hairspray. The big problem there is that, yeah, hairspray does help. It's a little bit tacky when you put a part down. It does help adherence to the first layer when you're using ABS, but you invariably get overspray, right? And right next to all these print beds are usually belts, screw drives, mechanical components that you're just coating with hairspray time after time after time. So the first 10 times you use it, no problem, works great. Then, you know, maybe on the 15th, maybe on the 20th, your mechanism seizes up, halfway through a print, you've got a serious issue because now you have hairspray coating all the innards of your machine. So that's the root problem there. It's better to just kind of stick with some sort of tape or different kind of material that you think is good. One of the drawbacks is that, especially on our single filament printers, they do automatically generate support structure. Say you were building a statue with the guy's arms hanging out. If you just started 3D printing stuff, you're going to get spaghetti. Without support, it's going to end up like this guy's face on the right. Just the flashing's going to kind of go everywhere. There's going to be no structure supporting it. So you actually have to build this like truss work, a lattice that's automatically generated for you. You don't have to mess with like cleaning the model unless you want to. But it will support the arm, it will support whatever overhang you have. Perhaps you're doing some sort of architectural model that needs that. But whenever you pull that support structure off, you invariably have that little patch of plastic that didn't come all the way with it. So you have to sand it off, you have to cut it off, whatever post-processing tedium you have to get involved with. That's one of the drawbacks. One thing that's killed a lot of student projects is a tangled filament roll. It's spool up on the back, and invariably, once you put it in and out of the cabinet 7 times, it gets a little bit of overlap in it and it gets tangled up. And then your print head becomes like a dog on a leash. It tries to move to a certain spot, and the steppers miss a step, and then you're completely offset the rest of the printing time. So far all these, it's really easy to overcome. The worst case so far has been that somebody has to restart their print. We haven't killed a 3D printing machine. What's the gentleman's name who introduced us today?
Ed?
Ed. Yeah, Ed said, don't blow up a 3D printer, but they're made of plastic and metal. So if you blow one up, tell me. That's cool. It's going to be kind of hard. Now, if you burn down OSU, I can see that being a little bit more possible. And that's why whenever we get to the rules, which I think are coming up next, yeah. Let's see here, which rule we're talking about? 3. Rule number 3. Machines must be babysat by at least one person at all times. Just basically so we don't burn OSU down. That's really the only risk you have with these things, unless you somehow get your face caught underneath the hot end with, I don't know, a heater in your eye or something. You'd be impressed with what students pull off sometimes. But anyway, first on the list, computers down there. We have computers set up, and since they're open access, you don't have to log into them. They're just for 3D printing, they're just for this space. They re-image themselves just like the library every time you restart it. So don't write your dissertation on these computers and then restart it, expect it to be there. It's gone. Some of you are really good with computers. I'm sure you can bypass that system, but just please don't mess with it. These printers bought with student money, set up for us. So that's just our method of kind of keeping things tight, keeping things clean. So printing area right now is not classified as a lab space, and that's intentional. We want to differentiate it from labs where you have to sign up and get certification, go through training, and blah, 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 all these other things to be able to use them. As we develop a reputation for safety with these machines, and the executives and the deans see that people aren't going to lose arms, 3D printers, hope them to be even more open. So any time during the day, you just go check out one of the machines and use it. In fact, we're very close to that at this point. That means that you don't really need safety glasses right now. These machines are fully enclosed when you print. They have a lid on the top, door on the front. So again, if you get plastic splattering in your eye, that's an achievement. You should get points for that or something. On down the list, we've already covered 3. 4 is that whenever you're doing research, whenever you're doing something for your own project, please use the machines. If it's OSU related, please use the machines. But bring your own filament. We have supplies of filament over there for engineering design. That's purchased primarily for the class. I mean, if you're in a research group, you see the small part, sure, we'll hook you up. We've got oodles of this stuff for now. But that material is supposed to last multiple years. So it's not that expensive, like $35 for a kilogram of the plastic. I have started using one spool from the time we put the machines together last spring. Actually, the spring of last spring. It's not gone yet. I'm maybe 2/3 of the way through it now. I've printed quite a fair amount. No single team has burned through an entire spool yet. So all the projects you see outside of 108, all the projects you see are now featuring the student union, they're all within the spool. So the easiest way to calculate how much you're going to need is by weight. Whether you're working in SolidWorks or whatever else, set the material to ABS plastic, see how much your part weighs, and then you know if you have enough. While we're discussing it, an easy way to avoid tangles in your part is to cut off the length you need. The software I'll show you later, in fact, somebody remind me if I don't tell you where it is, tells you how much filament, how long the piece of filament you're going to need to print. It'll tell you need 240 centimeters, or you need 4 times around the earth, like this. Solid knowledge of your mom. It came on my head. All right. Anyway, clean the machine in the area, fill and scrap after use. You'll see some of the machines over there right now. You open up the door, there's going to be scrap all inside. It's kind of annoying, it's just a mess. It's not going to affect anything badly, but it's just cleaning this, taking care of our environment, showing that we, not like the Earth environment, but taking care of our working environment. Show the school we actually do care about this being a safe and repeatable thing. No post-processing of parts on the tables. It means like you know, keep the knives away, don't gouge the tables, don't sand on the tables. You know, I'll say this, you know, 5 times or whatever, but students will still do it. I understand the desire to, but the outcome is invariably that somebody somewhere, you know, like sands a hole through the finish of the table, and that knucklehead kind of, you know, ruined the nice looking lab. Right now it's new tables, new everything down there, so it looks pretty slick. Try to keep looking that way. Yeah.
How are you keeping the filament in the lab from oxidizing? Doesn't PLA kind
It's
of
shipped
expire?
in a vacuum seal. And that's very important. Yes, PLA absorbs water. It's hydroscopic. So as soon as you open up the vacuum sealed bag, PLA has a shelf life. Like I mentioned, that roll of
That's why I was confused when you said it should last like 3 years.
Yeah, it's vacuum sealed.
Okay.
Yeah. Once you expose the PLA, in fact, some are vacuum sealed better than others, so I'm questionable that stuff. But it's also a matter of spending the money when you have the money. Yeah, back to what?
Length of time, how long do they last?
Once the spools are out?
Yeah.
I can't give you an exact number on that. The spool that I opened in January, I still printed on yesterday. That's the material that you see being passed around the little OSU.
Do you store it anywhere after you use it?
I store it back in the cabinets we have down there. I mean, ideally you'd vacuum seal it again to prevent it from absorbing as much water.
Or those, like, I've seen people use the balls, like the stuff that says do not swallow that
Yeah.
comes in random packages.
This stuff tastes really good.
You can throw that in the aqua fit of pancakes.
Yeah, exactly. Just anything you can do to help it to keep from absorbing water. If you put it in a dehumidifier cabinet, that would help. Whatever package you bake, and what it does is it gets brittle. It's more like the filament starts snapping. I don't think it's so much that it won't melt, that it won't make a 3D part. It's just that the spool becomes very stiff and stops unrolling as well. In fact, that spool that I have that I'm still using, it's almost a year old now. Yeah, it's kind of showing its age. Anyway, 7 OSU owned machines are for school projects, research, and OSU related activities. Like I mentioned before, I think everything started. One of the goals of the lab is to set up an accessibility environment so that, you know, we don't find some Joe down there printing a shot glass at 3:30 in the morning, you know, after he's not on the strip. That's not really the intended purpose of it. And lastly, one thing we're going to get into with the next slide specifically, is that all prints must be PG, you know, whatever incarnation you might think of where that'd be a problem. But the thing that I tell my students, and I just tell them to deal with it and not argue with me, but I'll justify it to you, is that I don't want to print, and the school doesn't want you to print any weapons of any kind, things like knives, you know, even those plastic, actually, after cutting myself a couple times with these parts, you'd be surprised they can actually hold an edge, surprisingly, for at least enough to cut you. No projectiles, firearms, or components of firearms, because we've all heard a ton of news stories about nothing bad actually happening, but, you know, the news media blowing up about the subject, right? We've got a whole slide prepared for this. Again, this is a subject I typically avoid with my class, but with you guys who are here just for 3D printing, and this is such a big topic with 3D printing, and especially the public relations side of 3D printing, we gotta go over it. In fact, one senator has even proposed licensing 3D printers. Anytime you wanted to go buy a 3D printer, you have to apply for a license for it, you have to have all your prints documented. So what? Okay. But anyway, to cover things first, yes, you can make a gun that works and shoots and works just fine. In fact, it might be better than the other 1911s you make with a 3D printer. Solid Concepts did it just to prove they could. Every component except for the springs was 3D printed on one of their DMLS printers, one of those high-end $850,000 printers. So that is, if you bought a printer just to make a gun, that's one of the most expensive guns on the planet. But 3D printing at its core is just a manufacturing technique. As you see down there at the bottom, at the very bottom of the screen, this is also a gun from Lowe's. That's like, you know, a $17, what they call a zip gun. There are multiple incarnations of those from that level of simplicity all the way up to, you know, mock AKs, automatic weapons made in people's garages. So the thing I want to stress, without getting into the theology of guns, whether it's right, whether it's wrong, I put just 3 points that if people start discussing this with you or asking why we can't print that stuff out at OSU, first of all, it's because we don't want the media coverage. We don't want people saying that we're developing the OSU armory or anything. Manufacturing personal firearms goes back all the way to 1288. The first guns were homemade. It's easier and cheaper to make hardware stores zip guns. You're going to be buying a 3D printer to make a plastic whatever that might hurt someone. You've just wasted money. I don't know. Anyway, there's way more troubling things you can do in a garage with materials and chemicals available to us. I mean, go through any one of the chemistry labs over there and you're more dangerous than a 3D lab. Some really nasty stuff working around these places. Including but not limited to the 5-gallon bucket of mercury that was discovered in Mobile in 80 labs. Whoops. So anyway, any questions discussing that specifically? Because I think at this point we'll take questions first. We'll have a break, get pizzas, drinks, whatever, and we'll show you repeat your vote. All right, I think we're pretty much back, right? All right, with your return, we can keep going. So this software that you see is running on my poor little netbook, so forgive me if the laptop is a bit slow. I don't have admin access for this, so we was very unhappy to install Meteor Host. The software is free. This version you're seeing here is the SolidDual specific one. So if you want to put this on your laptop and go down there and plug in through USB to the printers, that'll work just as well as if you want to use the desktop computers that are already over there. So, very first thing you do with Meteor Host is going to be connect to the printer. This operates through USB to serial conversion, so I mean, you use this on probably a lot of other kind of projects like Arduino stuff. If you ever mess with that, it's actually a serial signal, but it's carried over USB. So by default, you can check printer settings, and by default, over there it should say COM3 or COM10. It should have some virtual COM port in this menu. Right now, I obviously do not have a free printer connected, so it says virtual printer. This is actually an emulator for a printer, so it'll accept the signals generated by Meteor Host and act as though one is connected to my computer, so you can see how things are working. So it's actually super simple to just get a print going. So I'll cover it first, then I'm going to hop into some of the advanced things you can cover with Slicer and manipulate some things for you. So very first thing when you go over there, you just turn on the printer, connect your power supply, whatever else, and you click connect. Next thing you do is load, just next down the menu, and this part is accessible through OSU's OC.OKState website. There's the way you get certification for this lab. In fact, just doing this class doesn't put you on the list. You have to pass a safety quiz that those rules should pretty much help you pass entirely. You can take it as many times as you want. You just have to, it'll tell you which questions you get wrong. You just have to keep taking it until you get 100%. And that is a self-enrolled course on OC.OKState. You know all the self-enrolled things you can drop into? It's called C3 Printer Certification and Training. So you self-enroll in that course, take the quiz, and then whenever we have this checkout system either set up in the library or through the dean's office, they'll be able to reference your name on that list, see that you're good, and hand you over the power supply to go turn on the printer. That's theoretically how that checkout system is going to work. So in that same 3D printing training certification self-enrolled course on OC, you can find the sample STL file. That's how they look. This is kind of the output of SolidWorks. Oh, there we go. The output thing of SolidWorks after it's finished making the part itself. You can see that I've kind of this little chamfers on the edge, made the logo. You know, just basically took a two-dimensional logo, made it kind of a nice 3D looking stamp thing. You've all seen the part that just dropped on the floor. And you got to pass it around, so this is your source file. The scale of 1 is this piece. I believe this one is a scale of 1.5. And just changing that will take from 20 minutes to about 40, 45 minutes. So the time starts to leak away from you pretty quick. So by default, you saw that I had to rotate it by 90 degrees. That's because the coordinate system that I saved in SolidWorks was wrong. Had it tilted the wrong way. That's really not an issue because you can rotate this however you want. You know, you can rotate this 90 in the other way and print it out like that if you just want it to take forever. Interestingly enough, this is a good opportunity to ask the question or just support the point that this would take support structure. If you try to print that out without support structure turned on, you're just going to have spaghetti. The molten plastic can't support itself. It's definitely just going to seek the lowest energy state, and it's going to droop down and make a mess. So obviously keep things flat, keep things quite level. The guiding angle is 45 degrees. Anytime you have an overhang greater than 45, you're fine. If you have something that's 35, 30, 20, that's going to be a problem. They can't self-support. So even 45 sometimes becomes a little bit precarious. So regardless, let's move this guy back. It's important to keep things centered on the print bed. Sometimes you'll even, in importing a part, it'll sink below 0. Anytime you do that, you just click center object, and I'll put everything back towards the middle. In fact, if you want, you can load multiple files in at once. You can put a couple of these guys. You can have different things, you can have the same thing, whatever. You can either auto position, which manipulates things and maneuvers them so they don't interfere with each other. You can center things, just make a whole array of parts. Generally, I've found it less reliable doing it this way, because any one of those three instances, even if they're all the same thing, screws up. You just run all three instead of actually just running one. It doesn't save you a whole lot of time either, unless you just want to use your personal printer and leave for the night. Just leaving for a night with these printers isn't really an option. That being said, if you need to print off a lot of things, you might as well use, if we have 10 printers, use 6 of them, and make 6 different things you want, since you can watch them all at the same time. So regardless, bring things in, center it, make sure it's the size you want. All STL files should be saved as millimeters, as the default scale. If you save them as inches, it's going to come in either be way too big or way too small, depending on which direction things are scaled. You can always change it back though, just by putting in the conversion factor between inches and millimeters up here. Notice also the lock aspect ratio button is clicked. If you wanted to go in and actually make this a little bit squatty, you can do so. You can mess with the aspect ratio of things, but honestly, after spending so much time in SolidWorks or another 3D printing program, make it look just how you want. It's kind of blasphemous to sit there and mess around with it. So, let's go to Slicer. This is the actual piece of software that basically the rest of this is kind of a GUI for. Slicer is what takes the STL file, which is really nothing but a point cloud with directions on how to connect the dots. STL files are very simple 3D text files to understand, not by looking at it because it's just numbers, but for computers to understand how they're structured. Really generic settings, you just make sure that, well, in this case I want SolidDoodle 0.3 millimeter. That's the thickness of the trace you're setting this G-code up for. This is where you can select the thickness. 0.3 is what I suggest you use today. We are going to be using the SolidDoodle 8x8, which is what the SolidDoodle 4 is. 8x8 print bed, also 8 inches tall. They have different material settings, different filament settings, ABS or PLA. Most likely what we're going to print with for improved success today is PLA material. So all of this is 1.75 millimeter. If you're going to buy your own roll on Amazon, make sure your roll of filament is 1.75 millimeters in diameter. The other alternative is 3 millimeter, which is used for larger printers to put more plastic down faster, but 1.75 is the dominant size for most small-scale desktop 3D printers. So whatever, basic settings. Once you set these once on the computer, in fact, the ones up there should already say all this stuff. You just mash the slice button. This poor netbook's going to try its hardest to perform this task for us. Usually it takes like 5-6 seconds. It's not usually very involved unless there's a problem with your STL file. Unfortunately, SolidWorks does reasonably often create problems with STL files. I'm kind of surprised that it does, because otherwise it's a pretty high quality product, but SolidWorks just gets choked up. It will leave essentially holes or voids in an STL. There's a website you should write down and take note of called cloud.netfab.com. This is a cloud service offered by, I would call them a big-time STL or 3D design company. They have software you can license for like $400 a year, using an academic term. They let you open up STL files, manipulate points, and really just make them look really good. We don't need all that functionality. All we need are the holes and mistakes that SolidWorks sometimes, maybe I would say 10%, 5% of the time, will screw up an STL setting. If you upload it to this cloud service, their servers look at your file, say, oh, that's where it derped out, fixes it, and will send it back to you to download. So it's actually nice. It's free. You have to have, I think, a Microsoft account to use it, because they bought this company out, seeing how sophisticated the software was. But that so far has worked to fix problems with STL files that SolidWorks has made. All right. So we've sliced it, and this is what things come up with. You actually see a preview for the first time of every individual trace that you see in the window. If you get in really far, you actually see how it's going to fill in the different letters, how it's going to make the actual pieces. This is the point where you should review the part to see if you had a problem with the STL. You'll also see warnings down here in the text, but sometimes they go by so fast that, and you're not paying attention to the text down here because that's, gosh, it's boring, where do you sleep? Then you're not going to notice the actual error message down there. So look to see that the shape you see pictured here is what you want. This shape is generated by all the coordinates and codes stored in the G-code over here. So all these lines, all 16,710 lines, dictate the shape of what's going to be made. So that is where you want to check your shape. Check curved surfaces to make sure that it turns square or whatever else. Remember where I said it will tell you how much filament you need? There it is. Bottom of the G-code. It hides it from you, but it's handy. It's all the way down here. This part will take 1.6 meters. If I can do that right. It tells you the total volume, as well as a predicted printing time. 16 minutes, 34 seconds. One thing I tell you is, That's wrong. It's probably gonna take like 20. Generally give it like 20% to 30% extra time over what it predicts. It just does it based off of total length that the printers have to move, the total print distance, and the printer itself doesn't hold constant speed across that path. So this prediction doesn't take that into account. So at this point, with everything else set up, you could just mash the button assuming your printer was ready, and it would go. But we should mention a couple of other things. Conveniently enough, as you scroll down this, you notice these bars on the left change color. The first one being kind of a mild green. That's just kind of all your setup parameters. Then it goes into this dark green. This is your first layer. If you scroll down, this one's going to go back to mild green. That indicates, oh, there it is, the next layer change. So if you ever want to see where one layer stops and one layer starts, that's where it happens. The first layer always has provisions to put in special G code at the beginning and end of it. At the end of the first layer here, you see that it sets the temperature again with a G code entry called M104. That sets the print head temperature. You can change it right there, though the better way to change it is in the slicer settings. So just keep in mind if you need to adjust that to make sure it's not going to set to something crazy, that's where you can check it to make sure. Also, the default print temperatures are up here at the top. Again, back millimeters up to the coordinates. Yeah, the default temperatures, whenever you get over there, actually not using a virtual printer. We store right here at the top of it. You can check to make sure if you're printing with PLA, you have to make sure the G code does not print with the print bed heater turned on. You set that temperature to 0 or remove the line entirely. And you can check to make sure that it's printing PLA at 190 degrees Celsius. That's the temperature that works best for the material we have. So remember that number. Again, like I said, it's always best to kind of scroll down and check the end of the first layer again, because if you get through the first layer and all the temperatures stay fine, you're pretty much going to be surfing gold for the rest of the period. So just make sure it doesn't accidentally turn the print bed on again down here, and then you pretty much click and forget the printer after that. Those are kind of advanced things, hopefully stuff you don't have to check very often, it's just nice to verify. This manual control is where you can move the print head around, well, manually. It's kind of an interesting arrow system here. If you click the very inside, you can move it in the negative X direction 0.1. So if you mash that, the printer will react to the serial command. You hit this next increment out, it'll move 1 millimeter left in X, 10 millimeters left in X, or 100 millimeters. So be very careful whenever you click a portion of these arrows, because if you accidentally, if it's 30 millimeters away from the wall, you mash 100, well, you just cause the stepper motors to skip a bunch and you have to re-zero it. Zeroing the machines is easy. It happens automatically every time you start a print. It has switches on X0 and Y0, so whenever the print head gets to that location, the switches actuate, opening the circuit, and the printer knows, like, ah, I'm home. If you want to force it to do that manually, these are actually buttons. The most stealthily hidden buttons that took me like hours to find in this stupid software the first time I used it. So you hit X home, Y home, and that machine will center itself at X0, Y0. Also, you have a Z home button. This is actually very important to make sure that the print bed itself is level and is set to a good 0. If the print bed is too far down to the print head when you start printing, it's just going to be like pouring spaghetti out and it's not going to stick anywhere. If the print bed is too hard up against the print head when you start to print, it's going to like be scraped across the print bed and not work well either. So you want, ideally, and the technical term you see in Soldiers' website is you want the plastic to smush, technical smushing of the plastic on the first layer to make sure it adheres reasonably strong, but it's not just dropping onto the print bed and also certainly not obstructed by coming out. I can show you the dial on the printer once we get over there, but look for the limit switches in X and Y, and especially the limit switch in Z. Also, the print bed itself is a tripod. It's suspended on 3 sprung thumb screws. All these print beds over there should be level, they should be fine. It's very seldom that one gets completely thrown out of whack. But if your printer is just doing really bad, come get my attention and we'll help you out. But you can adjust the level of the print bed with those thumb screws. It's best to set the Z0 and just move the print head around and then adjust the thumb screws until it sits properly at the level 0 that you want. So, I suggest when you get over there, even right after you connect, come to the manual control tab and turn on heat extruder. On this virtual printer, you should see this go up reasonably quick. So you're still connected. Yeah, 24. Does it move at all? I don't think it's 20. But on the virtual one, it's very slow. On the real one, it's even slower. So this heater takes a while, especially the trip from about 150 to 190. So you can prescribe the temperature of the print head right here at any time. Even while it's running, you can change the print head temperature by typing something in that window. Even while it's running, you can turn on the heated print bed by mashing that button. Set that to whatever temperature you want. Generally for ABS, 105. That'll turn the print bed on. Keep in mind the print bed itself has a lot of thermal mass. So once you turn it on and it gets hot, if you made a mistake and you don't want it on anymore, or you're waiting for it to cool down after the part's done, it's going to take a few minutes. Because there's not really strong convection inside of this print box to let it cool off. So another command that's very useful is extrude and retract. These are useful whenever you're adding the filament into the printer. So before you print, you actually have to load the spool in, and to do that, you actually have to make the material that has been stuck in the old print head and has been cut off molten. Otherwise, you can't pull it out; it's stuck, right? It's in the shape of this triangular arrow thing in the print head. You can't pull it back out. So once this gets up to temperature, up to 190 degrees, you can extract the old filament, the little nub that's left in the printer, by clicking the retract button. You mash that once, it'll back it up 10 millimeters. You'll see the little stepper motor actuate. It'll push that plastic out 10 millimeters per click. One thing I've seen students do that's just a nuisance for the students, I don't care, but if they click this like 10 times, it's going to sit there and queue up 10 commands. Since it's a serial interaction, the machine waits until it's finished executing the previous command to see what's next in the buffer. So if it's not responding, or if it's still like lowering the Z table and you're clicking a ton of things, you're really just building up another buffer of commands. So try not to click on new things until the old operation's finished. It's not reacting very quickly. The worst thing you can do is sit there and continue to click buttons. So extract the old filament once it's warmed up. Remove it, a few millimeters at a time. Put the new filaments in. You just mount the spool in the back. There's a hole in the back of the printer. You feed the little thread of plastic through. Shove it down in the hole the old filament came out of. And then you just click extrude, waiting for the stepper motor to stop after each click until you start squeezing plastic out of the print head. We have little squeezers over there. We have stuff you can use. It'll make a little bit of a mess, but it's not going to stick too hard. It's easy to pick up. It cools down very, very quick because it's a very thin filament with high convective coolant. So that's how you load filament. That's how you extract the old stuff. Once your print head is up to temperature, all you have to do to get it going is just mash run job. In fact, in this case, it's waiting. And in your case, in there, it will also wait until it hits the prescribed temperature. So you see down here, it's reading out 112 and 190. The very first G-code command is to tell the printer not to try to extrude anything until it's hot enough to do so. Because otherwise you could damage the part. It's actually one of the self-protection things of the machine. So that's one way you can really kind of script stepper motors or anything else. Trying to mash plastic through that extrusion head that's not above the glass transition, which is not going to go. As you see in this situation, the simulated print is going, and you'll see the real ones go along with it over there. Gives you a kind of a depiction of which parts of the filaments are still hot, which ones are not. I wish it went this fast, but it's not working. So, at this point you're printing. Whenever it's done, the extruder will go back to its home position. The print bed will drop, and we have spatulas over there, or you can just peel up the masking tape and pop the part off. And you're finished. Questions? I'm sure there's a ton of things I didn't cover. We will go over kind of some of the advanced settings in Slicer, but out of the things I just went over there, you guys think you have a pretty good recollection? Some of my TAs that volunteered their time tonight are going to be over there to help us in the 3D lab. So if you have questions, raise your hand. We have experienced people there. They're going to be there to advise you. I'll be down there myself as well. But before we, I don't hold you guys up very long. I want to make sure you get plenty of time to print. Let's go over some of the configurations of the Slicer, some of the basic things. Also keeping in mind that the instruction on this program, the stuff you just heard, and some of the advanced subjects we'll cover with Slicer are covered in videos on that 3D printing website on OC. So if you forget everything, if it's just you're having a brain dump right now, you can go back and rewatch and re-listen to all of this, and unfortunately my voice still, online at that OC website. So this is the actual settings of Slicer. The interface actually cuts your part into layers. The default layer heights and everything else you probably don't want to mess with too much, but the default thing you want to mess with the most, or you'll be in here changing the most frequently, is support material. Whether or not your slicing operation will generate it at all. So if you check that box, it will automatically generate support material for any overhang that's greater than 40, or I should say, angled less than 45 degrees. If you have a slope of 45, the assumption is that the material will be self-supporting. So you can change that threshold right there in slicing. Raft is a set number of layers that will actually elevate your part above the print bed. Say the bottom side of your piece is critical for whatever reason. Raft will build support structure of however many layers you specify to elevate that piece off the print bed. This can help if you have a warped print bed, if you have a naked, for whatever reason. I never use it. I haven't had a need to. This is where you change the support material and raft's size and shape. You can have support material shaped as a honeycomb. Rectilinear grid is probably the best option that I've used, or rectilinear just means straight lines. Rectilinear grid is nice because it stacks lines, every other layer is 90 degrees offset. So that means that the only contact points holding your support structure together are where they cross. It's very, very easy to just grab that support material, rip it off the part, and then you're good to go. Even though it's still the same plastic, it's very, very easy to pull off. Other things to look at, infill. If you need to make a solid part, that's where you come to. Right now it's set to generate infill automatically with honeycomb. It'll be that little honeycomb pattern. You can change things here again, different kinds of infills. But if you change this to a density of 1, you all of a sudden get a solid part. So you are building something out of plastic and you do need it to be strong. Come here first and set the infill to solid. That way it will not put void space inside of your part. Be heavier, take longer to print, whatever. You need it strong, that's the best way to go. One example of this is that one of the printers over there you'll notice the inside of the printers, there's a lot of 3D printed parts. Printers again making more printers. One of those parts broke. It was just faulty. It was a part that was under bending load from the factory. It actually had 2 or 3 of them break, so I just drew them up in SolidWorks, printed out new ones, fixed their problem and their mistake, and ours is better than everybody else's now. So I actually printed a replacement part for the other printers with our printers for circular. So doing that, so you need to strength, I set it to solid infill and orient it in a way that the part behaves more like a composite. I suppose that's one thing I haven't really mentioned, that one very important characteristic of FDM material is that the weakness is not the plastic itself. The weakness is the joint between layers. That's the very, very weakest part of the entire thing. If you're used to dealing with composites and directional strength, you're going to be better at 3D printing. They're strongest along the direction of the filament itself. If you're pulling something where all the layers are coming apart, if you're trying to pull like a phone book, it's not going to stick together very well because the joints between them, because one layer is already rather cool, when the multi-layer gets deposited onto it, that's the weakest bit. All right, some other things worth mentioning before we just go over and start playing with these things are skirt and brim. Skirt lets you put a larger footprint on your part. You've heard me talk about in the presentation that one of the hardest things to do is make sure the parts stay stuck down. Say you're printing a 3D print of like a deer. Even if it has all 4 feet on the ground, their feet aren't very big compared to the rest of the print, right? So if you turn on skirt, that's basically going to put the deer on coasters. It'll basically print a circular coaster around each foot, increasing the surface area it has for adhesion to the print bed. That'll help it stay stuck to the bottom better. You can specify how many loops you want it to make, and how far, actually this is brim we were discussing, how far the brim needs to be made around from the bottom of the thing. Skirt is actually, in my opinion, most useful as a print head priming device. Once these things get warm, they'll kind of dribble some plastic. It's used liquids mostly, so you'll see them drop plastic out every so often. So when you start the print, there's often void space inside the print head. The first, however many millimeters don't actually get plastic shoved out on. So one way these printers account for is by putting a skirt around the printed object. It puts essentially just a ring around it. So by default, it puts 1 loop around it. If you wanted to make sure your print head was good and primed, you got that to 5 loops, 7 loops, whatever. Just to make sure that by the time you actually start making the part you care about, the print head's primed, it's flowing properly, and the skirt you end up throwing away. Keep in mind that every time you change some of these settings, if you restart the computer, back to defaults. So, important to check to see if the default has the support structure turned on or not. Again, if you don't have anything that's overhanging by more than 45, doesn't matter if it's on or not, it's not going to generate support structure for you. Questions on this? Yeah.
Can you save the slicer setting to a flash drive?
You can. By default, in fact, I should mention that if you make changes, be sure to click Save. And save it as some sort of setup in there. You can go to File, Export Config, and assuming it didn't just crash on me, probably did. You can export your configuration as a text file. It's config INI, just did it on the other machine a few minutes ago. But, yeah, I'll save it as a text file somewhere. Perfect, that installation's worked. Yeah, you can export the thing, no problem. Other questions? You guys ready to go do this? All right, let's go, see you over there.